Hello all, I welcome you to in this another video tutorial in the series of computer system architecture, and in this lecture I am going to explain you about the full subtractor, and we will start with the definition of full subtractor along with its truth table, the boolean functions, and the circuit design. So what is a full subtractor? Full subtractor is used to subtract 3 binary bits, or we can say that full subtractor is used to subtract 3 1-bit numbers x, y and z that I have already write down all the combinations of these 3-bit numbers, right, which are x is minuend and y is subtrahend and z is like borrow, right? So these are the 3 1-bit numbers that we are going to subtract using the full subtractor. Full subtractor is also a combination circuit like the half subtractor and the half adder and full adder. Full subtractor has 3 input states which are x, y and z, and the 2 output states which are difference and borrow. So here I write the borrow and difference. So these are the 2 outputs that a full subtractor gives to us. So in the first case, when we have x0, y0 and z0, in this case when we are going to subtract these numbers, so we will get the difference is 0 and the borrow is again 0 because all the 3 numbers are 0. But in the second case, when we have x minus y minus z, so read like that, x minus y minus z. So first of all do x minus y. So when you do x minus y, it evaluates to 0 because both are zeros, and then y minus z, 0 minus 1, which is 1. So difference is 1, but in that case borrow is 1 because I have explained it in my previous video of half subtractor, in which I explained you that why this borrow is here, because 0 minus 1 means 0 minus 1. That means we need to borrow something from this side, so otherwise we cannot subtract it in that way. Okay, so if it is a number, assume that there are many numbers, many binary digits are exist, so in that case we have to borrow 1. Okay, so this thing you need to remember, right, to understand it very clearly, right? Again in this case when we have 0 1 0, so when x is 0 and y is 0, y is 1, sorry, so 0 minus 1, which it will be, again we need to take some borrow like in this above case. So we have 1 borrow, and 1 minus 0 is 1, so that's why difference is 1, right? So the difference is 1 but the borrow is 1, right? And now in this case when x is 0 and y is 1 and z is 1, so in that case 0 minus 1 1, 1 minus 1 is 0, so the difference is 0 and the borrow is 1 again, because when you subtract x minus y, when you subtract y from x, so in that case you have to take some borrow. So what will be the borrow? Borrow will be 1. Okay, so because the 1-bit number, right? But in this case when consider this 1 0 0 means x is 1, y is 0 and z is 0. So in that case what would be the difference? Difference will be 1 minus 0 1, 1 minus 0 1. So the difference will be 1, but here you can see that we don't need to take a borrow, so the borrow will be 0. Same in this case, when 1 minus 0 is 1, 1 minus 1 is 0, so the difference is 0 and the borrow again will be 0. Okay, here 1 minus 1 is 0 and 0 minus 0 is 0, so the difference is 0 and the borrow will be 0. But here in this case, when we have 1 minus 1, so because x is 1 and y is 1, so x minus 1, x minus y, so 1 minus 1 will be 0 and 0 minus 1. So this is the case of this case 0 1. Okay, so 0 minus 1, again the difference will be 1, but we need to take the borrow, so the borrow will be 1. So the borrow and the difference will be 1. So now this is the truth table of the full subtractor, and when you when you want to draw a boolean function for this, so you need to draw a Karnaugh map for borrow and the difference individually. So for borrow, I am considering for borrow firstly, and then I will explain the Karnaugh map for the difference part. So the borrow is, again in this case we have this 1, here we have 1, and here, and in this case, so we have the 4 cases when we have the value 1 for the borrow part, right? So let's consider that where we have to place these ones in this Karnaugh map. So I have already divided this K map into 8 cells, because I know that these are the 3 variables. So when we have 3 variables and we need to draw a Karnaugh map, so in that case we have to put the value of n is 3 here. So in that case we will have 8 combinations, so 8 cells in the Karnaugh map. So here when x is 0 and y is 0 and z is 1, so x is 0, y is 0 and z is 1. So this is the case, so we have to put 1 here. And for this one, when x is 0, y is 1 and z is 0, so x is 0, y is 1 and z is 0, so we have to put 1 here. And when we have this case, again x is 0, y and z are 1, so x is 0 and y and z are 1, so this case, so we have to 1 here. And in this case, when x is 1 and y is 1 and z is 1, so x is 1 and y is 1 and z is 1 is here in this case. So this is your borrow part. And when we are going to grouping, so this is the same as the full adder. So right, so what we have to do, we have to make a group of 2 adjacent cells, as we know that right. So as we know from the K map that we need to make a group for 2 evaluative boolean functions for this case. So we have 3 groups here, as this is the same of like full adder carry table or carry truth table, right? So here we have these 3 groups, and for these groups we have to evaluate the expressions. So this is so simple, because if you are paying attention to these tutorials, you know that how to read these and how to evaluate the expressions for these combinations, right? For these combinations we have x is common, so we will write x complement here, right? X complement, and then because 0 1 1 1, okay, 1 is common here, so 1 common is like if you don't know how to read these, you can watch my previous videos. And for I just to remind you, this is z is common and y complement plus y will be 1. So here we have x complement z plus Then we have this 1 1. Okay, 1 1 means yz, so we have directly write the yz. And then for this these two last adjacent cells we have 1 1 1 0, so 1 y is common, right, from here, and here from here x complement is right, so we will write x complement y. Okay, and so now for this part, which is the difference Karnaugh map. So for this we have to evaluate this by placing the ones here, right? So 0 0 1, so when x is 0, y is 0 and z is 1, we have 1. When x is 0, y is 1 and z is 0, we have 1. When x is 1, y and z are 0 is 1. So these are the 4 cases we have 1. So place it here. So at 0 0 1, so 0 0 1, this one will be here. 0 1 0, this one will be placed here, and then 1 0 0, so x1 yz 0 0, this one will be here, and then again 1 1 1, we have 1, so at this place. So this is same as the full adder sum Karnaugh map, right? So we can directly write the because there is no grouping, and we can directly write the x XOR and y XOR plus y XOR y XOR z. So this is the we can write directly, because we know from our previous lectures that this will evaluate to it will be a XOR gate between these three variables, right? If you don't know, please do watch the video of the full adder. I have explained it in very clearly that how this is possible and how this is this expressions is come out. And now we have to make a logic diagram for this. So the logic diagram is very easy for you, because you know that this is the sum of product form, and for B we have x complement z. So x complement z, x complement, so we need to use a inverter to invert the x. So x complement, and then we have this z. So this z is again feed it to the AND gate, as we know that there is a dot operator, or we can say that there is dot operation between the x complement and z here. So we know from the definition of AND gate, right? So this is x complement z, and then we have next is yz, right? So just y and z, okay, y and z. So from here we can see that this is for yz, and again we have to use the AND gate for this expression. Then we have this x complement y, so x complement y, so x is from here we can take, and y is from here, right? So we have this x complement y, and then we have the plus symbols between these products. So again these three are fitted into a OR gate, right? Into a OR gate. So this is your, so this expression is your for the, right, for borrow, right? And for the D part, which is your difference parts, we have to just fed these three variables, or three x, y and z into this XOR gate operation, right? So this is your XOR gate. Let's make it like that, okay? X, y and z, this is like, right? Okay, now this is your XOR gate, and x, y, z are fitted into this, and it gives in output is D, right? And here we got the output B, right? So this is your logic circuit for the full subtractor, right? So if you have any query regarding these this concept of full Subtractor, please let me know in the message box. And if it is beneficial for you, so please let me know. Thank you very much. Thank you.